Hello my dear students, welcome to IMS GATE Academy foundation course on digital circuit subject. So in this particular session we are going to start the second chapter, that is Boolean algebra and K-maps. So all of you kindly share this video link with all of your friends. This particular topic is common for all the four branches: EC, electrical, instrumentation and computer science. In the last class we have discussed regarding the last topic of the first chapter, that is related to binary codes. We have discussed what are the types of binary codes available, and then we have discussed regarding BCD code, XS3 code and gray code. So regarding these codes we have discussed in detail, and how to find the corresponding codes, etc. we have discussed, and we have discussed variety of questions also regarding these concepts. And in the first chapter we have discussed regarding the various number systems and how to do the conversion of a number from one number system to another, and how to find the basic arithmetic operations like addition or subtraction in any number system. And then we have discussed the questions related to how to find the base or radix in both conventional approach and shortcut approach we have discussed. And then we have discussed regarding data representation for unsigned case and signed case, etc. And then we have discussed regarding binary codes. So all of you, suppose if any of you couldn't attended regarding the first chapter digital circuit subject, so kindly watch those sessions in your free time. It will help you a lot for all of you. Regarding the first chapter we have covered the basic concepts in both. What are the questions we have discussed? We have discussed in both conventional approach and shortcut. Hello student, good evening. Yeah, regarding canonical SOP, canonical POS, yeah, regarding those conversions we will discuss in the tomorrow's session. Yeah, we will discuss. Today we are going to start the second chapter. So all of you kindly put the heading, the second chapter, that is Boolean algebra and K-maps. So regarding Boolean algebra we will cover in 3 sessions, and regarding K-maps we will discuss in 2 more sessions. Okay, total I will discuss regarding chapter 2 in 5 sessions in our YouTube live. Okay, so all of you kindly put the heading, that is Boolean algebra. So here you're having one word, algebra. So I hope all of you might have studied in your engineering mathematics like matrix algebra or linear algebra. So in general sense, what do you mean by algebra? All of you kindly share. In general sense I am asking. Yeah, good evening Pragya. In general sense I am asking, what is algebra? I hope some of you are already attending Maths Gate Foundation course in our YouTube channel. Okay, so those who couldn't attended, so kindly watch those sessions. Priyanka madam used to discuss regarding the first chapter, matrix algebra, currently going on. Okay, right. So algebra means it is very simple. You are performing some sort of operations, right? So suppose if you are considering matrix algebra or linear algebra, there you are performing some mathematical operations on matrices like addition, subtraction, inverse, determinant, etc. So many operations related to the matrices, right? Here you are having one more word, that is Boolean. So here you are having one mathematician, his name is George Boole. He has developed this particular algebra. So accordingly the name Boolean algebra has come. Okay, here what are the conditions are there, okay, regarding the variables and what kind of operations we can perform. Here we'll discuss one by one in detail. Okay, so just make the definition regarding Boolean algebra. A mathematician named George Boole has developed an algebra which involves the variables that can be represented in one of the two possible ways. In one of the two possible ways or two possible values. Yeah. So here you are having one mathematician. His name is George Boole. He has developed this particular algebra. So according to the name, Boolean algebra has come. Here you are using some sort of variables, but those variables, one mandatory condition is there. That is what? That particular variable can have only two possible values. Say for example, if you are considering, like you are having one statement, if that statement is true, then you can say it is true, or if that statement is false, then you can say it is false. Okay. So you are having one statement, you can identify whether it is true or false. Okay. So that means you are getting only two possible values. Okay. Similarly, say for example, you are representing electrical signal. Okay, if you are representing that particular signal with only two possible values, like 0 volt and 5 volt, 0 volt and 5 volt. So here this is 0 volt and this is 5 volt. Suppose if you are operating, okay, only at two voltage levels, 0 volt and 5 volt, here if you observe, you are having two voltage levels. Among these two levels, which one is higher? 5 volt is higher, okay, when compared to 0 volt. And when compared to 5 volt, 0 volt is what? Lower. So that means in terms of logical, you can say this is logic high, this is logic low, right? Logic high, logic low. And in general, we will consider 0 volt as bit value 0 and 5 volt as bit value 1. In terms of bit values, 0 volt we will consider as 0 bit value, 5 volt as bit value 1. So in this way, whatever the variable you are having, that variable, if you can represent one of the two possible ways or two possible values, that time only this particular algebra will be applicable. Okay, right. Now let us see what kind of operations we will perform in this particular algebra in some time. So before going to discuss that point, whenever you want to design any circuit, especially digital, okay, so that time according to your required specifications, based on the specifications you will determine how many inputs you require and how many outputs you will require. Okay, and then you will write the input combinations in terms of zeros and ones. For each and every combination, you will write the corresponding output value, either 0 or 1 based on the requirement. And then we will represent each and every output function. Okay, you will, regarding that, how to represent the functions, what are the various functions are for a particular each and every output variable, how we can represent with respect to the Boolean definitions or rules, etc. That topic we will discuss in the tomorrow's class. And whatever the Boolean functions you will get, we have to implement those functions, right? So that means inside any digital circuit, you are having one main component. Can you guess what is the main component inside any digital circuit? Or whatever the Boolean functions we are going to discuss, okay, those Boolean functions, in order to implement, what components we require? Yes, obviously you require logic gates. Yes or no? Correct. Logic gates we require, right? So that means inside any digital circuit, the main component is logic gates. Yes, very good, logic gates. Now, with this understanding, just can you answer this simple question? It is a very simple question. It is a MCQ question. Only one option will be correct. All of you give a try. Yes, very good, very good. Option C is the correct one. Option C is the correct one. So up to now what we have mentioned, whenever you want to design any digital circuit or if you want to implement any Boolean function, we have to use the logic gates, right? Inside any logic gate, the main component you will be having is transistor. Inside any logic gate, you will be having the main component is transistor. So transistor is having lot of applications, among which according to our regarding this particular chapter, okay, if you want to correlate, we can use transistor in one of the application. With the help of transistor, you can turn on or you can turn off, okay, based on the requirement. You can close the switch or you can open the switch, like that, okay. So that means we can use transistor as a switching action, switching application. Transistor acts as a switch. We can use transistor acts as a switch, okay. There are number of applications like amplifiers, oscillators, etc. There are number of applications with the help of transistors. Here currently we are going to discuss regarding transistor, one of the application, that is switching action, okay. With the help of transistor, you can make on or off, like that. So that's why whenever in the circuit diagram, if you are having transistor, just you can represent the transistor with the help of single switch. You can represent the transistor with the help of single switch, like this, okay. So that means if suppose if the switch is closed, then we will say it is what? Closed position or on. Or if the switch is open, that means it is open or open position, like that, okay. Switch close, with the help of switch we can do two actions, either closing or opening, right? So that's why here if you observe once again, transistor we can make it on or we can make it off. Just observe here also you are getting one of the two possible cases, either transistor are on or transistor off. That's why here if you observe, just like true, false, 5 volt, 0 volt, logic high, logic low, 1 or 0, that means two possible values, right? In the same way, with the help of transistor, you can make are there. That's why we can use the same Boolean algebra even as well, right? So here we are using transistor as a switch. So according to this one, you are having one more name for Boolean algebra, that is switching algebra. From on state to off state or off state to on state, we are switching the transistor, okay, right. So now let us see here, when you are having single transistor, so accordingly you will be having single switch, okay. Suppose if you are having two transistors, okay, so equivalent we can represent, okay. Basic configurations I am showing here. Try to identify these configurations belongs to which cases, okay. So for the time being I am considering two switches. So this is one configuration. So for the time being I am considering two terminals 1 and 2. Similarly here also two terminals 1 and 2. So what is the first configuration? What is the second configuration? Can you guess? I have considered for the time being two transistors. So just now I have mentioned wherever you are having in the circuit transistor, we can just simply represent as switch. Okay. For the time being, I have considered two transistors. This is one configuration. This is another configuration. Can you identify how these two switches are connected and how these two switches are connected? Yeah, you can observe here. Yes, very good, very good. Series and parallel. Yes, very good. So here if you observe, I have considered two switches. For the time being, I am labeling switches as A and B. A and B. I am having two switches. For the time being, I am labeling as A and B. Suppose if you want to connect terminal 1 to terminal 2, if you want to connect terminal 1 to terminal 2, then both the switches must and should be closed. Then only the terminal 1 we can connect to terminal 2, right? Similarly, here if you observe, you are having, if you want to connect terminal 1 to terminal 2, you are getting three possible ways. Okay, suppose if you are closing only switch A, then that time terminal 1 is connected to terminal 2, or if you are closing only switch B, then also terminal 1 is connected to terminal 2, or you can close both the switches. You can close both the switches, then also terminal 1 will be connected to terminal 2, right? So here we are saying both the switches must and should be closed. Okay, right. So that means here you are having series connection. Here we have connected the switches in series, and here we have connected the switches in parallel. Parallel connection. Parallel connection, right? Now, here we are saying that if you want to connect terminal 1 to terminal 2, both the switches must and should be closed. That means here we are using one operator among A and B. Between A and B, we are performing one operation. What is that? Here both the switches must and should be closed. That means here we are using one symbol, that is the dot, logical AND symbol. Logical AND operation we are performing. Logical AND operator. And similarly here, among these two switches, we can perform one logical operation, that is A plus B. Here we are performing plus symbol, here indicates logical OR. Logical OR operation we are performing. Whenever you are having any big circuit or system, there you will be having in the combination of series and parallel or parallel series. Okay, it is a very big network, but that network you can break into small parts like this. Okay, it will be in the combination of series and parallel. Whenever you are having series configuration, that time you can use logical AND operator. Whenever you are having parallel configuration, that time you can use logical OR operator. Now you are coming to get the clue what kind of operations we can perform in this particular algebra or in this entire digital circuit subject. So here you can perform the logical operations, logical AND and logical OR operators. Logical AND and logical OR operators. Whenever series configuration is there, equivalent circuit you can represent among the variables as logical AND. Whenever you are having parallel configuration, that time among the variables you can represent logical OR operation, right? So with this understanding, just try to answer this simple question. All of you read the question and try to answer. Yes, very good, very good. Option C is the correct answer. Option C is the correct answer. See here in this question, you are supposed to identify the unary operator. Unary means you have to perform the operation on the single operand or single variable. Okay, if you are performing one kind of operation on the single variable, single operand. if you are performing an operation on the single operand or single variable, then we will call it as unary operator. Okay. So regarding not operation, see, in general, if you are having variables like a, b, this is the normal form. Normal form. The corresponding complements, you will be having a bar, b bar. So here, if you observe, this bar indicates what? Complement or not. Not operation or complement. Not operation or complement. So this particular complement operation you are performing on the single variable or single operand, right? So that's why not operator is an example for unary operator. Not operator is an example for unary operator. Now with this understanding, can you identify regarding AND operator and OR operator? In the previous example, we have used AND operator and OR operator. So these two operators in this particular example come under example of which operator? These two operators come under the category of which operator? Not operator come under the unary operator. So these two operators come under the example of which operators? Yes, very good, very good. Binary, it is very simple. Here, if you observe, we have considered two variables. Among those two variables, we are performing one operation. Whenever you are performing any operation on two variables, okay, so then that particular operator we will call it as binary operator. Binary operator. So logical and logical OR, these two are the examples of basic binary operators. Basic binary operators. So in this way, whenever you are having very big system or circuit in terms of digital, whatever might be the complex circuit you might be having, if you want to represent in the Boolean function format with the help of these three operations, you can represent in a Boolean function, okay, with the help of logical AND, with the help of logical OR, and wherever required you can use the complement of the variable, right? So that's why any digital circuit or system you can implement with the help of these three logic gates, combination of AND gate, OR gate and NOT gate. We can implement any digital circuit or system. That's why these three gates we will call it as basic gates, okay. So regarding logic gates we will discuss in next chapter. So here I hope all of you got the glimpse of Boolean algebra. So in this particular algebra, what kind of operations we are going to perform? So as of now, whatever we have discussed, these are the basic binary operators regarding whenever you are having two variables among which you can perform either logical AND or logical OR. Of course, we will be having some other logical functions or operations we can perform even on two variables. So those functions are those operators we will discuss later, but I am dealing currently regarding the basic. Whenever you are having two variables, among those two variables, what kind of basic operation you can perform? I hope all of you got the clarity. Logical AND and logical OR. Okay, whenever you are having single variable, you may require the help of NOT gate or complement. Okay, right. So with this understanding, now let us start the basic rules. Basic rules of Boolean algebra. Basic rules of Boolean algebra. Okay. So for the time being, let us consider one variable x. It is in the normal form, and the corresponding complement version is x bar. And in this entire course, we will use only two values, 0 and 1. Okay. So I am considering the constants 0, 1. Okay, right. So for the time being, I am considering one variable as x. And other variable can be one among these four. right. I have considered one of the variable is x, other variable can be one among these four. And just now we have mentioned that whenever you are having two variables, among which either we can perform logical AND or logical OR, right? These are the two possible basic binary operations, right? So for the timing, here I will consider logical AND, here I will consider logical OR. So here x into x, you will get x. Say for example, if you are assuming x as 0, 0 and 0 is nothing but 0. Or similarly, if you are assuming x value as 1, 1 and 1 is nothing but 1. So that means whatever the variable you have assumed, finally you are getting the same variable. Okay. So x into x bar, you will get 0. See, if x is 0, the corresponding complement is 1. 0 into 1 is 0. Or if you are assuming x as 1, complement is 0. 1 into 0 is 0. X into 0 is nothing but 0. X into 1 is nothing but x. Here we have performed the logical AND, you will get like this. Okay. Similarly here, let us perform logical OR operator. Here x plus x is nothing but x. Say for example, if you are considering x value as 0, 0 plus 0 is 0. Or if you are considering 1, 1 plus 1 is 1. Here we are performing logical OR operator. Logical OR operator, 1 plus anything is 1. Okay. Similarly here, can you guess what is the output you are going to get for x plus x bar? All of you quickly respond. What is x plus x bar? Yes, very good, very good. X plus x bar is 1. See, if you assume x value as 0, here x bar will be 1, 0 plus 1 is 1. Or if you are assuming x value 1, x bar will be 0, 1 plus 0 also 1, right? X plus 0 is nothing but x. X plus 1, how much you will get? Here plus indicates logical OR operator. Once again, just like here we have mentioned, 1 plus anything is 1, logical OR operator, right? So x plus 1 is 1. So here I have considered logical AND, here I have considered logical OR. Okay, right. Say for example, if I am considering two numbers 1 and 1, so here I am discussing for three cases. See here, in the first case, suppose if you are assuming both are decimal, if you are assuming both are decimals, if you are performing addition of two single ones, that means resultant output you will get 2 in the decimal form. 2 is the corresponding decimal. Suppose if you are assuming these two numbers are in the binary, if you are adding two single bits and if both the bits are having 1, then the resultant value 2, how we can represent? We can represent 1 0. So when you are adding two single bits, if both the bits are 1, then the resultant sum, in order to represent, you require 2 bits, 1 and 0, right? Now here, in the first case and second case, here plus symbol is corresponding for addition operation. Addition operation. Whereas here I have used same plus symbol only, but here context is logical OR. Logical OR operation. So 1 plus anything is 1, logical OR. 1 plus 0 is 1, 1 plus 1 is also 1. Logical OR operation. Okay, I hope all of you got the clarity regarding these three cases. Okay, right. So for the time being, here I will label, here we are having 4 equations. I am labeling like A, B, C, D. And similarly here I am giving the numbering 1, 2, 3, 4. Okay, here we are having 4 equations, here also we are having 4 equations. Just observe these arrow marks, and what is your observation point, tell me. And if you want, you can observe reverse way also, either from left to right or from right to left. Either you can see like this or in the opposite way. According to the arrow direction, you can observe in the forward or you can observe the backward. Okay. See, if you are having one of the equation in this set, you are going to get one more equation of this particular set in order to get like this. Or if you are having one equation of this set, if you want to get the corresponding one more equation in this set, okay, what are the modification if you do? You can get either this equation or this equation. If you are having this equation, you are going to get one more equation here, or if you are having one equation here, you are going to get the corresponding one more equation. I am not saying that both are equivalent, but we are going to get the corresponding one more equation. From this pair, from this set, if you are taking any one of the equation, you are going to get the corresponding one more equation. Or if you are considering any of the equation here, you are going to get one more corresponding equation here. But those two equations are not equivalent. Those two equations are not equivalent, but there will be corresponding equation. In order to get like that, what kind of modification if you do here, you may get here, or if you do here, you may get here. Any observation point? Just observe the arrow marks. Just observe the arrow marks, and either from left to right you can observe, or from right to left. Any direction you can observe. Yes, it is very simple. You can observe here in this entire set. We have used what? Logical AND operator we have used. We have used logical AND operator, right? And here we have used so in the left hand side set, in this entire set, we have used only one operator, that is logical AND. Whereas here we have used logical OR. Logical OR. Wherever logical AND is there, if you replace with logical OR, that is the first observation point. Similarly, reverse also. In here, since I have considered only two variables, here in this entire set, I am having only one operator, logical AND. Similarly, here in the entire set, I am having logical OR. Suppose if you are having three variables or more than that, that time you may be having combination of both logical AND and logical OR, right? Here we are starting with the basic equations, and then slowly we are increasing the number of variables. Okay, right. Yes, very good, correct. Okay, the first and foremost observation point is wherever logical AND is there, if you replace with logical OR. And similarly, if you are having logical OR, you can replace with logical AND, vice versa. Okay, this is the first and foremost important point. And then, okay, so regarding first equation, you will get, it is very simple. If with the help of this one, you are getting first equation. Now just carefully observe regarding second equation. Here logical AND is there, here logical OR, no problem. Now here you are having 0, here you are having 1. So that means we have to interchange zeros and ones. We have to interchange zeros and ones. Okay. Here in place of 0, keep 1. So that means you are getting this equation. Similarly, you can observe this equation. Here you are having 2 zeros, here 2 ones. Okay. Here you are having 1, the corresponding, in place of 1, you keep 0, like that. So these are the two important observation points. Okay. So that means according to Boolean algebra basic rule, that means whatever the variable you are considering, if that variable we can represent with one of the two possible values like 0 and 1 or true or false, logic high, logic low, etc. Only one of the two possible values. With the help of that basic definition, if you are able to write one Boolean function, then if you just interchange the basic binary operators. The basic binary operators are logical and logical OR. The first step is you have to interchange the basic binary operators, and then you are having two constants, 0 and 1. So 0 and 1 you have to interchange. If you do like that, then you are going to get one more equation, and it will applicable with respect, it will satisfy the basic Boolean algebra condition. Okay, but those two equations are not equivalent. But what I mean to say, if you are having one Boolean function with the help of Boolean algebra basic rule, okay, if you are able to define, or if you are having one Boolean function, you are going to have one more corresponding Boolean function. Okay, provided if you do these two operations, if you do these two operations, then you are going to get one more the corresponding Boolean function, right? So can you guess what is this particular principle, or what is the overall law, whatever the two steps we have done here? Okay, so regarding that, can you name what is the principle of operation that we are going to what is the basic principle of operation that we have done, if you are able to do these two things? Yes, that is duality principle. So all of you put the heading duality principle. Yes, very good. So just write the definition. It is very simple. By interchanging the basic binary operators, by interchanging the basic binary operators, so just for reference you can mention logical and logical OR. By interchanging the basic binary operators logical and logical OR, and by interchanging zeros and ones. By interchanging zeros and ones, we will get the corresponding dual function. We will get the corresponding dual function. By interchanging logical and logical OR operators, and by interchanging zeros and ones, we will get the corresponding dual function. Okay, right. So that means whatever the here set we are having arrow marks, so that means you are getting, since you are getting pair of equations, we can say it is a dual pair. Okay, here you can write a comma 1, b comma 2, c comma 4, and d comma 3. All these are dual pairs. So regarding the specialty of the dual function or significance of duality principle, okay, we will cover in the logic gates chapter. Okay, right. So with the help of duality principle, you can implement the logic gates, designing of the logic gates easily. Okay, if you are having one circuit diagram, if you apply dual, you will get one more equivalent circuit. Not equivalent circuit, you will get the corresponding circuit. The other circuit will be the dual of the first one, like that. Okay, so which logic gates are dual to each other, and the significance of dual, etc. more in detail we'll discuss in the third chapter, that is logic gates. Of course, in this particular chapter also, regarding duality, in the third session I will cover. Okay, right. So now let us discuss the laws of Boolean algebra. So far we have discussed basic rules, and then we have discussed the duality principle. Now with this understanding, let us proceed for laws of Boolean algebra. Say for example, if we are having two variables, if you are having two variables x and y, okay, if you are performing one kind of operation here among variables x and y, if you are going to get the same output or same operation, even if you are interchanging the variables order, here variables are x, y, but here I have interchanged the variables order, so I got yx. Here also, if I am performing the same operation, if I am getting the final, if both the equations are giving the same output, then we will say that particular operator is satisfying one law. Can you guess what is the name of that particular law? Say for example, here I am considering logical AND operator, so that one will satisfy. X and y is same as y and x. Even though if you interchange the order of the variables, you will get the same functionality. That means here logical AND operator satisfy one law. Can you guess what is the name of that law? Yes, it is commutative law. Commutative law. Okay, so just apply dual here. Just apply dual. So regarding duality, we have told the first and foremost is wherever logical AND is there, we have to replace with logical OR. Similarly, vice versa. Okay, here you are having simply logical AND, you can replace with logical OR. X plus y is equal to y plus x. So that means here logical AND operator and logical OR operator both will satisfy commutative law. That means you can interchange the order of the variables. There is no issue at all. The final functionality will remain same. Yes, very good. It is commutative. Now let us consider three variables. X, y, z. I am considering three variables. Okay. Say for example, here I am performing among y and z logical AND first, and then with x. Okay. This is same as I am performing among x and y logical AND operation first, and then with third variable, that is z. Okay. See, when you are having three variables like this, okay, here among the three variables I am performing the same operator, logical AND only. But first of all, I want to perform on y and z first, and then with x. Okay, here I am performing x and y first, and then with z. Whenever you are having three variables or more than that, okay, if you are having the same operator, okay, you can perform on any two variables first and then with third variable. Like that, if it is satisfying, then that particular operator will satisfy associative law. So here logical AND operator satisfies associative law. So just apply dual here. Wherever logical AND is there, you can replace with logical OR. So you'll get x plus y plus z is equal to x plus y plus z. Wherever logical AND is there, you have to replace with logical OR. Similarly, if you are having logical OR, you can replace with logical AND. But here in the center equation, we are having logical AND. Even in the center equation, we are having logical AND. So that's why we have replaced wherever logical AND is there, we have replaced with logical OR. Okay, right. So up to here, I hope it is clear for everyone. So we just discussed the basic rules, and then we have discussed duality principle, and then we have discussed regarding commutative and associative. Okay, right. Up to here, whatever the equations so far we have discussed, in the left hand side, we have used only one type of operator, logical AND. Here logical OR. Similarly, you can observe here only one operator, logical AND. Here only one type of operator, logical OR. Right. Now let us use combination of both. The next law, next law, you can put the heading distributive law. Here we are using combination of both the operators. So here I am considering x and y plus z. So here three variables x, y, z I have considered. Here I am performing logical OR and then logical AND. Okay, right. So it is just like your normal, when you are doing multiplication of two bracket terms, what you will do, the same procedure you can apply here also. X and y plus x and z, same. X and y plus x and z. Okay, right. So just apply dual to here. Wherever logical AND is there, you have to replace with logical OR. Wherever logical OR is there, you have to replace with logical AND. Okay, so you will get x plus y and z. X plus y and z is equal to. Can you tell what is the right hand side term you are going to get? Left hand side I have written x plus y and z. Can you just apply dual here and tell me what is the expression you are going to get? Yes, it is very simple. Here you are having xy. So here you can write x plus y. And then here logical OR, you can consider logical AND. Then x and z is there, you can write x plus z. Simple. It is very simple. X and y is there, x plus y. Here logical OR, logical AND. Then x and z is there, x plus z. X plus z. Okay, right. So see, up to here, up to this particular equation, I hope there is no doubt for anyone, but some of you might be having doubt how here LHS and RHS both are equal. Okay, if you are having any doubt, it is very simple. Just consider right hand side term. Just consider right hand side term. Right hand side you are having x plus y into x plus z. X plus y into x plus z. Okay. See, just like here you are having single variable, but here you are having two variables. What we have done? X into y plus x into z. In the same way, for the time being, assume that there is no y. There is no y. Okay. If you are having only single x, then you follow just like here, apply the same procedure. X and x plus x and z. If you are having only single variable, regarding that we already discussed. Follow the same approach. X and x plus x and z. Okay. Now just ignore regarding x. Okay. You consider only y is present that time. Y and x plus y and z. Okay. When you are having single variable, how you will proceed? Follow the same. Like that, consider variable by variable, like that. Simple, very simple. Here in this case, we are having two variables. That's why we have considered with the help of first variable, two terms you got. Similarly, with the help of second variable, you got two terms. Similarly, if you are having third variable, then with respect to that, you will get two more terms like that. Okay, right. So x and x is nothing but x plus x and z, you can copy as it is. Y and x, we can write it as y and x we can write it as x and y, because logical and operator satisfies commutative law, right? So you can write x and y plus last term you can copy as it is. Now from first three terms, whether we can take anything common? From first three terms, whether we can take anything as common? Just observe. X is common, right? In all the terms, x is same. So you can take x as common. Then 1 plus z plus y. X into 1 plus z plus y. Now can you tell what is the overall value here regarding 1 plus z plus y? 1 plus z plus y. You can observe here. Here I have mentioned that 1 plus anything is 1, logical OR operator, right? 1 plus anything is 1. So in a similar way, here z plus y value, it could be 0 or it could be 1. Okay, if you are considering it is 0, 1 plus 0 is 1. Or if you are assuming this overall value as 1, 1 plus 1 also 1, because it is a logical OR operator, right? So that means the overall here bracketed terms you are getting simply 1. So x and 1 is nothing but x plus yz. Now just observe whether this expression is matching to here left hand side. Yes, it is matching. So we have considered the right hand side term and we have done the simplification. We got the left hand side. So that means both the here in this equation, whatever left hand side, right hand side terms you are having, both are equivalent. This equation is equivalent. Okay, I hope all of you got the clarity. Okay, so based on the requirement, see whatever the laws that we are discussing or basic rules, laws that we are discussing, these basic rules and laws will be helpful while you are doing the simplification of any Boolean function. Okay, right. So based on the requirement, if you are having if you are having the expression like this, you can write the expression like this, or if you are having the expression like this, you can write expression like this. Because just now if you carefully observe, I have considered the right hand side term. After doing simplification, I am getting left hand side term. So it is very simple. See, regarding that, just observe, with the help of that there also you can apply. It is very simple. Here x and y plus z, how we are writing x and y plus x and z, right? In the same way, x plus yz is nothing but x plus y and x plus z. X plus y and x plus z. This is the forward approach. Suppose reverse means right hand side to left hand side. It is very simple regarding that. So here you are having x plus y and x plus z. Suppose if you are having the expression like this, while you are doing the simplification of any Boolean function, if you come across the representation like this, how to directly write the expression like this? Regarding that, I am giving the approach. It is very simple. Just carefully observe, in both the brackets, you are having x plus something. In both the brackets, x plus is same, right? So copy that term as it is, and then here you can perform logical AND. That's all. X plus yz. I am repeating once again. In both the brackets, whichever common part is there, write that common part first, and then among the remaining terms, you can perform logical AND operator. That's all. So based on the requirement, we may use LHS to RHS regarding distributed law, or even we can use RHS to LHS also. Based on the requirement, we can use that one or this one. See, if you are not familiar regarding RHS to LHS, you will write 2 or 3 steps like this. After doing simplification also, you will get the same thing. But if you are able to directly write like this, you can save the time in your GATE exam. So this is the very important thing. So you will get familiarity when to apply this kind of LHS to RHS or RHS to LHS, etc. You can become familiar if you follow our lectures thoroughly. Okay. Okay, right. Now with this understanding, all of you try this simple question. This is the MCQ. Only one option will be correct. Yeah, it is very simple. Here you have to apply distributive law. You have to apply distributive law. Yes, very good, very good. Option D is the correct one. Yes, very good. Option D is the correct one. See, just now we have discussed regarding distributive law. If you are having x plus yz, you can apply distributive law like this: x plus y into x plus z, x plus y into x plus z, right? Apply same formula, same distributive law you can apply here. Here you are having a plus a bar b, a plus a bar b. So here you will get like this: a plus a bar, that is your first term, and then a plus b. X plus y into x plus z, in the same way a plus a bar and a plus b. So regarding a plus a bar, it is very simple. You will get 1 into a plus b. So 1 into x is nothing but x, where x is nothing but a plus b. A plus b. So option D is the correct one, right? So regarding distributive law, you will remember, okay, it is very simple. Based on the context or requirement, you can use LHS to RHS or RHS to LHS, and just based on the application of distributive law, LHS to RHS, regarding this one, a plus a bar b, a plus a bar b, you can directly remember this one as a formula. Or even if you apply the distributive law, after doing 1 or 2 iterations, you will get the same answer. Okay, it is very simple. You can do whatever the distributive law logic is there, you can apply in your mind. It is very simple. Here a plus a bar, you will get 1. So that means you will get a plus b, that's all. So here we are having only one variable b. See, just carefully observe, this is a very important thing. Here whatever the equation here we have discussed, okay, this equation even it will applicable for other variety of expressions. Regarding that, carefully listen this point. Here you are having one variable normal, here you are having complement. Okay, after that here you are having only one variable b, but here in place of b you can have like c plus d, there also it will applicable. Okay, so or you can have like cd is like product term, c plus d is like sum term or logical term. Okay, you can have instead of single variable here, you can have any product term or you can have any sum term also. Okay, so a plus a bar is 1, so you will get a plus whatever the other term you are having, that other term you will get. Simple logic. If you are having suppose cd here, you will get cd. If you are having c plus d here, you will get c plus d, like that. Okay, so that means it can applicable the distributive law here whatever the other than this condition, like here one variable normal, other variable is complement. After that, here whatever the term you are having, for that term also it will applicable. Okay, if you are having single variable or 2 variables or 3 variables or whatever the number of variables, there also you can apply distributive law. Okay, it is very simple. You can remember this one also as a like formula. So while doing the simplification, most of the time wherever required, you can apply regarding distributive law LHS to RHS or RHS to LHS, or you may get the expressions in this particular format. So if you are having the format of this particular function like this, you can directly write the equivalent function like this. Okay, regarding other basic rules and laws that we have discussed, I hope all of you are very much familiar. Only you may feel that regarding distributive law, in order to apply or regarding distributive law application like this formula, you may be feeling like, first time you are getting the idea of this particular distributive law and how to apply this distributive law in order to solve the questions. You will get the familiarity. Okay, no issue at all. Just continue our classes. You will get the familiarity when to apply distributive law LHS to RHS or RHS to LHS, or even the application of distributive law like this. Okay, you will get familiarity, right? Now, so far we have discussed the basic rules, and then we have discussed the basic laws like commutative law, associative law, distributive law, and duality principle. So far we have discussed. Now can you guess what is the most important and powerful law of entire Boolean algebra? Can you guess? What is the most important and powerful law of entire Boolean algebra? I am eagerly waiting for your answer. What is the most important and powerful law of entire Boolean algebra? Yes, that is consensus law. This is one of the most important and powerful law of entire Boolean algebra. Consensus law. All of you put the heading. This is very, very important. Very, very important. So first write equation xy plus x bar z plus yz is equal to xy plus x bar z. Xy plus x bar z. Okay, similarly, if you apply dual, you will get x plus y into x bar plus z into y plus z is equal to x plus y into x bar plus z. Okay. See, regarding consensus law, you should not remember or you should not by heart the equation. Okay. There will be some conditions. Regarding that, I will discuss. Okay, in some time. For the timing, let us see the proof for this equation and then we'll see the proof for this equation. After that, I will disclose the conditions. Okay, right. So consider LHS. LHS, you are having xy plus x bar z plus yz. See, whenever you are writing conventional exams in your BTech semester exams, okay, especially whenever you are having the questions like derive or prove, okay, so in the question itself you are having answer, right? So it is very simple. Just observe here you are having left hand side expression. If you observe, you are having 3 terms, okay. Right hand side expression you are having 2 terms, right? Somehow or other you have to do some manipulation, okay, and in order to get the 2 terms like this, okay. Just if you observe carefully, LHS, RHS, the first term is same, second term also same. That means the third term is missing in the right hand side. Third term is missing in the right hand side. So somehow or other we have to eliminate, or we will do some manipulation here in order to eliminate this particular term. Okay, let us see what kind of manipulation we can do in order to eliminate this one. Let us see. So the first 2 terms you can copy as it is, xy plus x bar z. Now here you are having yz, okay. So this product term you can multiply with 1. When you are multiplying with 1, resultant value will remain same. Resultant value will remain same. X into 1 is nothing but x, okay. Here you are having yz, yz into 1 is nothing but yz. Now just all of you quickly respond. Whatever the basic rules we have discussed, from those basic rules try to identify this one how we can write in terms of x. We can write this one as x plus x bar. Yes or no? X plus x bar is nothing but 1. Now first 2 terms you can copy as it is. Then here just perform logical AND. X and y and z plus x bar y and z. X bar y and z. Now just observe from first and third whether we can take anything common. Similarly from second and fourth whether we can take anything as common. See, from first and third you can take xy as common. Then you will get 1 plus z, 1 plus z. Then from second and fourth you can take x bar z as common. x bar z if you take common, you will get 1 plus y. 1 plus y. Now tell me, what is 1 plus z? What is 1 plus y? What you are going to get? 1 plus anything is 1, logical OR operation, right? So 1 plus z is 1, 1 plus y also 1. So xy into 1 is nothing but xy plus x bar z into 1 is nothing but x bar z. So now just observe this equation and here right hand side, both are same or not? Xy, yes, xy plus x bar z, yes, we are getting same, right? So we have considered the left hand side equation and we have done the simplification in order to get the right hand side equation. Okay, so for that what we have done, it is very simple. Since first two terms are same, I have copied first two terms as it is. Okay, in few iterations I have copied as it is, and here I have simply multiplied with 1. That 1 we have written as x plus x bar. Okay, after that I have observed the common terms and I have done simplification. Finally we are getting the first two terms as a simplified function. Okay, so we have seen the proof for this equation, and since this equation both are dual to each other, okay, if you blindly apply dual for each and every line, you will get the proof for this equation. Yes or no? Okay, so all of you just apply dual for each and every line. Just apply dual. So first consider the left hand side term, that is x plus y, x bar plus z and y plus z. And here also if you observe, left hand side you are having 3 terms and right hand side you are having 2 terms. Those 2 terms are nothing but the first 2 terms only. That means here somehow or other we have to eliminate the third term. That's all. Okay. So just if you apply dual for each and every line, you will get the proof for this one. Just like here, first 2 terms we haven't done any modification. So similarly you can copy first 2 terms here. Now tell me regarding the third term. Here I have multiplied yz with 1. Then the resultant term will remain same. Now just tell me regarding this one, what is the dual term? For 1, what is the dual? 0. For 1, the dual is 0. And here logical and is there, logical are y and z is there, y plus z. See, it is very simple. For any term, if you are adding simply 0, resultant term will remain same. Here I have multiplied with 1, resultant term will remain same. In the same way, here we have added with 0, resultant term will remain same. There is no modification. Okay, functionality wise equivalent. Okay, right. Now continue further. First 2 terms you can copy as it is. Now tell me, here you are having 1 we have written as what? X plus x bar. X plus x bar is nothing but 1. Now can you tell what is the dual of x plus x bar? Or how we can write this 0? See, x plus x bar dual is what? X into x bar. See, x into x bar is nothing but 0. Then you can write y plus z. See, x plus x bar, here you are having dual is x into x bar. After that logical and y and z. So logical are y plus z. Logical are among y and z. Correct? Okay. Proceed further. So here first 2 terms I am copying as it is. See, just apply dual. You will get x plus y plus z. Regarding x, y, z, you will get x plus y plus z. Regarding x bar, y, z, you will get x bar plus y plus z. X bar plus y plus z. See, regarding first two terms, since when you apply dual, you will get the same terms, right? Here, what is the first two terms you are having? Same. That's why I am copying first two terms as it is. Somehow there, some modification is happening in the third term. So accordingly, I am just applying dual for that one. Okay, right. So in the same way, here in this equation, the first two terms I have corresponding dual is nothing but earlier two terms. So I copied as it is. Now here I am getting two terms. XYZ dual is x plus y plus z. X bar YZ dual is x bar plus y plus z. Okay. Or even suppose if you are having equation this one, if you want to simplify or if you want to get this equation, it is very simple. First two terms I have copied as it is. Now carefully observe. Here y plus z you can assume like single variable p. Okay. You can assume the y plus z is single variable p. Okay. So now you are having like p plus x into x bar. See, you can observe here x plus yz. Here we have applied distribute law, right? You are having single variable here. Okay, x plus y into x plus z, right? Now in the same way, this y plus z I have considered like single variable or single term. Okay, now you can apply distribute law here. Suppose if you are assuming this overall term is like p, so you will get p plus x, p plus x. Okay, so regarding p as it is, y plus z, p plus x. Okay, similarly here p plus x bar, p plus x bar, right? Where p is nothing but y plus z. I hope it is clear for everyone. Earlier we are having single variable, now we are having two variables logical. So together you can consider as single term also. There also it will applicable regarding distribute law. Okay, when you apply distribute law here, from this particular overall term, you can bring to the two terms like this. Okay, I hope it is clear for everyone. If you are having any doubt, you can ask. I will repeat once again. Now, just simply apply dual for these two lines. You will get the proof for this particular equation. Here you are having xy, so you will get x plus y. Now tell me. Here logical and is there, here logical or. Now tell me, regarding 1 plus z, what is the dual? What is the dual term for 1 plus z? For 1, what is the dual? 0. And for logical or, logical and, z remains same. Okay, right. Here you are having logical or, that means logical and, then x bar plus z plus z. Same. Here logical and logical or, regarding 1 plus y, just like 1 plus z, the corresponding dual term is 0 and z. In the same way, for 1 plus y, the logical and term, you will get 0 and y. 0 and y. Okay. When you are multiplying anything with 0, resultant term you will get simply 0. When you are adding 0 to anything, the resultant value will remain same. Yes or no? When you are multiplying any variable with 0, you will get simply 0. Okay. Here also 0, here also 0. When you are adding 0 to anything, resultant answer will remain same. Okay. Right. So that means you will get x plus y into x bar plus z. X plus y into x bar plus z. So now just observe x plus y into x bar plus z. Yes, we are getting RHS. In this way, if you are having the proof for first equation, since this equation both are dual, simply if you apply dual for each and every line, you will get the proof for this equation. Okay, suppose since you are having the proof for this equation, simply we have applied dual, we got the equation. Suppose if you are having this equation, whatever the equation here you are having, suppose this equation if you are having, okay, suppose you are supposed to do the simplification of this particular function. Okay, after doing simplification, you are supposed to get this one. How to get, if you are having the equation of this one, how to directly write the expression like this? Okay, now I will give the shortcut. since we are having the proof for first equation, simply we applied the dual and we are able to get the final expressions this one. But in the exam, if they give, like in one of the question, if they have given this directly the Boolean function like this, and if they ask to match among the given choices to which option it is matching, like that. Suppose in one of the option you are having the expression like this, how to identify this is the equivalent for this particular function. Okay, from here how we can write directly this particular equation with the help of single step. Okay, regarding that I am going to discuss now. So all of you please pay attention. Okay, I will copy this equation and I will note down once again. So for the timing, if you want, you can give this equation numbering as 1. X plus y into x bar plus z x plus y into x bar plus z into x plus y plus z x plus y x bar plus z x plus y plus z and then x bar plus y plus z x bar plus y plus z. See, what are the equation earlier we got, I have written as it is. Now what are the equation? Suppose if you are having the equation like this, how to do the simplification of this one and how to get directly this particular expression. Regarding that, now I am giving the shortcut. It is very simple. Whatever the equation here you are having, just I am modifying like this. Can I write like this or not? All of you please respond. First term I have copied as it is. Now I am considering the third term. I am writing the third term. And then second term I am writing. Okay, after that I am copying the fourth term. Now tell me whether the first equation, second equation both are equivalent or not. Whether first equation, second equation both are equivalent or not. Same, right? You can observe. The first term I have copied as it is x plus y. Third term I have written here x plus y plus z. Second term I have copied as it is. Now in the last term I have done slight modification. Here x bar plus y plus z is there, but I have written here x bar plus z plus y. Okay, why I have written like this? You can get in short. Okay, you will get in short why I have written the slight modification here regarding this term. See, suppose for the timing, if you don't have these two terms, if you are having only these two brackets, then if I ask you to simplify this entire expression, what you will do? You will consider x, you will multiply with these three terms. Similarly, you will consider y, you will multiply with these three terms. Similarly, if you consider only these two terms, okay, then here also x bar you will multiply with these three, similarly z with these three. Like that, you will get some terms here. Similarly, you will get some terms here. After that, you have to continue once again. Just like here, you are having two brackets, here two brackets. In the same way, from these two brackets, whatever you are getting, the number of terms sum together. Similarly, here also number of terms sum together. You have to continue further, right? In order to get further simplified expression. It is a laborious process or it will take more time, right? Now I am giving the hint here. See, for the time being, now consider, just observe in the two brackets. In both the brackets, x plus y is same. In both the brackets, x plus y is same. So now you can assume x plus y as a single variable or single term. Say for example, if you are assuming x plus y as something like p, okay, for the timing, assume x plus y as p. then this expression how you can write? P into P plus Z. If you assume x plus y as single variable P, okay, here P into P plus Z. Now you just apply whatever the simplification earlier you used to do, follow the same approach. P into P plus P into Z. P into P is nothing but P plus P into Z. Now from these two you can take P as common, then 1 plus Z. 1 plus Z is nothing but what? 1 only. So you'll get simply P. So that means directly you can remember this is the formula. It is very simple. Suppose if you are having P into P plus Z, directly you can write that one as P. That's all. This one also you can remember as a formula. It is very simple. Okay, if you are able to write directly like that, you can save the time in the exam while you are doing the simplification of the Boolean functions. Okay, it is very simple. I am repeating once again. If you are having like this, P into P plus Z, P into P is nothing but P plus P into Z is nothing but PZ. So like that, whatever here we have written, you can just analyze or you can do like this simplified steps in the mind only. Okay, after that from these two you can take P as common. 1 plus anything is what? 1. So that means finally what you are going to get? P only you are going to get. That's all. That's all. If you are able to observe this particular key point, now if you apply that key point here, what is the answer? What is the answer? Here P into P plus Z is nothing but P, where P is nothing but what? X plus Y, simply X plus Y. Similarly, from these two brackets, in these two brackets, now you can assume X bar plus Z is something like P, or you can assume X bar plus Z is something like Q. Okay, Q into Q plus Y is nothing but Q, where Q is nothing but X bar plus Z. It is very simple, yes or no? Whether we got the same term or not, X plus Y into X bar plus Z, yes, we are getting the same term. So in this way, you can directly write the simplified functions easily if you are able to apply these small shortcuts, whatever we are going to discuss in this series of sessions. Okay, right? It is very important. Okay, so regarding distributive law, we already discussed, and even while you are multiplying two terms or two bracketed terms, from there also how to get the simplified function quickly. So first of all, instead of doing the simplification in the conventional approach, linear process, okay, instead of following that one, just observe the common terms. Just observe the common terms. Whenever few terms are common, just assume that entire common term as like single variable. If you are able to observe like that, and if you are able to apply like that, then you can get the answer. Just observe. Once if you are able to rearrange the expression, given expression like this, how much time it is required in order to write like this expression? How much time it is required? Couple of seconds, right? You can do this calculation, whatever the calculation here I have done, what are the two steps here, understanding purpose I have written here, but what are the two simple steps here you are having, you can just do this particular simplification procedure in your mind only, right? If you are able to, whatever the small steps or small functions if you are having, if regarding that simplification, if you are able to do in your mind, then you can solve the gate questions regarding digital circuit subject in less time. Okay, otherwise you can solve and you can get the correct answer, but it may take more time, right? So whether you want to solve the gate questions regarding digital circuit subject in less time or long time, you can decide. Okay, if you want to solve the questions regarding digital circuit subject in less time, you can watch our series of lectures regarding gate foundation course. Okay, regarding the basic concepts, you will get the complete knowledge and you will get clear concepts, and you will get conventional approach and shortcut approach. The shortcut approach help a lot in the gate exam. And of course, if you are not strong on the basics, okay, you cannot solve any gate question. So fundamentals are very important. That's why this foundation course help a lot for all the 4 branches: EC, electrical, instrumentation, and computer science, right? So kindly watch whatever the earlier session, if you couldn't attend it, so kindly watch those sessions also in your free time, right? Okay, so here we have discussed regarding the proof of this equation and proof of this equation, and with the help of duality we have derived, and even Suppose if you are getting the one equation like this, how to directly get this equation, regarding that also I have discussed the shortcut. Now this is the most important thing. What is that? Regarding consensus law, I mentioned that this is one of the most important and powerful law. Why I have told that one? Because in general students will by heart any equation like anything. Okay, but regarding consensus law, you should not by heart the equation. Rather, there are two conditions. If those two conditions are satisfying, you can bring three terms to the two terms. Okay, whenever those two conditions are satisfied, then only, okay, always there is a possibility to apply consensus law to bring three terms to the two terms, provided the two conditions are satisfied. Okay, what are those two conditions? All of you pay attention, it is very important. Okay, say for example, whenever you are having three terms summed together like this. Okay, now for the timing I have considered the last term. Okay, here what are the variables you are having? Y, Z, two variables are there. Y is present in this term and Z is present in this term. Here you are having three terms. Okay, now among the three terms, okay, I have considered the last term. Here you are having two variables Y and Z. Y is present in the first term, Z is present in the second term. Y can present in the middle term, Z can present in the first term. No problem at all. Whatever the variables here you are having, those variables should distribute in other two terms in any fashion. That means here Y is there, Y can present here, Z can present here. This is one combination. Or Y can present here, Z can present here. That is another combination. Suppose if you are having Y bar here, Y bar only present here. Okay, or Y bar can present here, like that. Suppose if Z is present here, Y bar can present here. Or if Y bar is present here, Z can present here. So that means whatever the variable you are having, exactly the same form. If you are having variable normal form, exactly normal. If you are having variable complement version, exactly same complement. Okay, that is the first and foremost condition regarding consensus law. Once that condition is satisfied, now you have to check the second one. Here what is the missing variable? In this term, what is the missing variable? The missing variable is x. That is present in one of the term as normal, in another term as its complement. See, x can present here, x bar can present here, no problem at all. Just like regarding yz I have mentioned, y present here, z present here, y can present here, z can present here. In the same way, x can present here, x bar can present here, no problem at all. I am repeating once again, these are the two conditions. Okay, whatever the term you have considered, regarding that term, whatever the variables you are having, those variables exactly same form, it should be distributed in other two terms, and whatever the missing variable is there in this term, that missing variable should present in one of the two terms as normal, in another term as its complement form. These are the two conditions. Once these two conditions are satisfied, then we can bring three terms to the two terms like this. That means this particular term is redundant. Redundant means even in the absence of this particular term, you can get the same functionality. That is the beauty of consensus law. Okay, so regarding consensus law, you should not by heart the equation. Okay, rather these two conditions, if you are able to remember, that is very simple. Always there is a possibility to bring three terms to the two terms, provided these two conditions are satisfied. Okay, right. So far, whatever the basic rules and laws that we have discussed, you can use any of these rules and laws whenever you are doing the simplification of any Boolean function. Now, if you want to find the complement of Boolean function, that time which laws we can use? Yes, we can use De Morgan's laws. Okay, it is very simple. With the help of De Morgan's law, we can find the complement of the Boolean function. So xy whole bar is equal to x bar plus y bar. And similarly, if you apply dual, you will get x plus y whole bar is equal to x bar and y bar. See, it is very simple. Under the complement, whatever the variables you are having, each variable will get complement. And then here logical AND is there, you will get logical OR. Okay, similarly here each variable will get complement, and then here logical OR is there, you have to replace with logical. Here you are having the variables, instead of x, you can have the product term or you can have the sum term. There also it will applicable. Suppose x is one sum term, y is another sum term. So there for overall term, okay, for first term you will get complement. Similarly for second term you have to apply complement. After that, if you are having logical and logical, or if you are having logical or logical, like that. That's all. Whenever you want to find the complement, that time you can apply De Morgan's law. And before applying De Morgan's law also, first check whether you can do any simplification of the function under the complement. If there is a possibility to do the simplification, first do it. If not possible, then only directly you can apply De Morgan's law. If there is a possibility, first do the simplification, and then if required, then you can apply De Morgan's law. Okay, right. So in this particular session, we have discussed regarding the base. We started from the Boolean algebra introduction, and then we have discussed the basic rules, and then laws we have discussed. Okay, so with the help of these basic rules and laws, we can do the simplification of any Boolean function. Okay, especially whenever you want to find the complement, that time we can use the De Morgan's law. Okay, so in this particular session, regarding the theory part or concept we have discussed, and even the shortcuts, okay, we have discussed. Those shortcuts will be helpful a lot whenever you want to simplify any Boolean function, or whenever you are attempting any question related to this concept. Okay, in the tomorrow's class we will discuss some questions regarding these basic rules and laws, and after that we'll continue further regarding the further topics. Okay, so kindly attend these sessions without missing. Okay, so these sessions are going to help all of you a lot. Okay, thank you everyone. For the time being, I'm stopping here. Thank you everyone. We'll meet you all on tomorrow's session.